Hello everyone, it's Mr. Joshi. I'm finally an undergrad student here at Kathmandu, Nepal, majoring in electronics and communication engineering, and my primary research interest lies in the field of machine learning, computational neuroscience, and computer vision. I was a student in Neuromass Academy last year, and this year I'm here as a TA, right? So today, on the third day of the first week, we'll be discussing about multiple linear regression and polynomial regression. So let's go into this, right? So before going deep into the stuffs, let us get to know what regression means. So regression is a statistical tool that is used to build relationship between two or more variables, right? So in regression, we have two types of variables. The first one is called independent variable, whose value you can set freely, and depending upon the value of independent variable, we determine the values of a dependent variable, or simply dependent variable depends upon the value of one or more independent variables, right? So yeah, let's go through this notebook. We'll import the required functions, right? And then let's talk about linear regression. In linear regression, you have this y is the dependent variable, which is expressed in term of x as y equals to theta x plus epsilon. Here theta represents the slope of the line, right? You can simply think of this as a line with slope theta and intercept epsilon, right? So this is the simple case, right? We might have more than one independent variables. In such case, we can write y equals to theta naught plus theta 1 x1 plus theta 2 x2. Here, each input feature is scaled by a certain parameter or a weight, and then we sum all those values to determine the value of y, right? And if we condense this equation in a simple form, we can represent it as y equals to capital X of theta plus epsilon, right? So here X is the design matrix and theta represents the parameter vector, which is a vector of length equals to D, where D represents the number of independent variables, right? So one thing to be noted here is the matrix notation is easier for us to implement in our code also, right? And another one is it makes the representation very simple, right? So X is the design matrix. So this is the design matrix. Here you can see the before every row we stack one, right? This is to account for theta naught. So here you can see y equals to theta naught plus theta 1 x1. So when one gets multiplied with theta naught, it becomes theta naught, and we can just get this theta naught term, right? So we stack one before every term. Okay, so now so in linear regression or regression, basically we determine the value of theta, and if we can get the value of theta, later on we can predict any value of y if we are given x, right? So our major purpose here will be to determine theta naught, and through this equation we can get value of theta naught. We are given x and we are given y, and we have to calculate the value of theta naught, right? So for this, to determine the value of theta, one of the major, most widely used method is ordinary least square estimator, and this is the expression for ordinary least square estimator. Now let's code these things, right? Okay, so we will use the NumPy library. Here we have inverse, right? So we'll use NumPy library to calculate inverse and other operation matrix related operations. So np dot linear, we have linear algebra module, and we have inverse function over there, and we will pass x dot t, which represents transpose of x, and at the rate represents matrix multiplication, which is multiplied with x dot t, and which is again in turn multiplied with x y. So we have a function which takes x and y and gives us theta, right? So yeah, let's comment this code because it will raise the not implemented error. Yeah, okay. So, and we'll print the value of theta hat that is estimated. For this, we need to Okay, so yeah. Sorry guys, I just forgot to explain this thing. So here we have y represented in the z-axis, and here we have x1 and x2, right? So you can see the data points, and we will try to fit a plane which passes through most of the data points, so that we can represent y in term of x2 and x1, right? So that's our sole purpose. And now let's run this cell. Oh, sorry. Actually, I haven't run this cell, so there was some error. So we get the value of theta naught, theta 1, and theta 2. So we have here three parameters, right? Because of we have two independent variables. So we'll have theta naught plus theta 1 x1 plus theta 2 x2 y equals to. So that's our theta matrix. Now, if we calculate the value of y, and here we are printing the value of MSE. So MSE stands for mean square error, which simply represents the error, right? So you have a plane, but all those points don't lie on the plane. So how these actual data points are uh, different from the values that we estimated, that is given by the MSE. More the MSE, the less accurate is our model, right? So yeah, let's visualize this thing that we did. So let's run this cell. So here you can clearly see we have two variables, x1 and x2, and we have this dependent variable y, and this is the plane that we fit. And these are the actual, these blue dots are the actual data points, but you can see the plane does not pass through each of data points, and you can see these small green lines that represent the error, right? So there is slight deviation between our prediction and the actual value of those points. So when we square these errors and sum up, this gives us MSE, right? So the next thing is polynomial regression. So